we're doing a graph neural network analysis of color center defects in silicon. My name is Pete Downey.
And I'm Logan Sipser.
Okay, so color center defects are essentially defects in a material with optical properties, so photons can go in and out. And these are really promising candidates to act as qubits in quantum computing. However, to find a color center defect with ideal properties requires really slow guess and check methods. Currently, just to run for one simulation requires about 25 hours in the GPU. What we want to do is we want to use a graph neural network to essentially screen candidates. So if we do inferencing, it predicts really bad properties. We can throw it out before we have to use these traditional methods, which are very computationally expensive. So how does what we're doing work? Essentially, we take a crystal defect structure, we convert it into a graph representation, we feed it into the network, and it's trained on a bunch of labeled samples, and then we predict the defect properties, we evaluate the performance, and then finally we've created a real-time inferencing model that allows any user to essentially put in the crystal structure and get out an inference in a few seconds.
So our model uses two graph attention layers that is then flattened and sent through three linear layers where each activation function is a ReLU, and it predicts the defect property from there. Initial results are relatively promising considering the complexity of the system. The performance greatly varies from property to property, with spatial values such as initial delta Q and delta R performing very well, but other properties such as CBM, VBM energy performing just moderately. So there's a lot of additional complexity we can talk about here, but if you're interested in the project, here are the links to the GitHub repository and the project website.